Right, hello everyone. Welcome to this talk, 13 ways of looking at a turtle. And I have a lot of things to cover in less than an hour, so I might go a little bit over. So a lot of the talks here are sort of deep dives into one topic. And I thought for fun, I would do one topic, lots of shallow dives. In fact, 13, maybe even 15 very shallow dives. And mostly they're going to be functional programming things. We're going to cover a lot of functional programming techniques, partial application, error handling, state monad, actor model, event sourcing, dependency injection, interpreter pattern, capabilities, and see if I can squeeze all this in because I've got 4 minutes per topic. So it's going to be pretty crazy. This is I did another crazy one on functional patterns. So if you like my crazy talks, then you can watch that one too. I'm going to be using F# for the code examples, but this stuff will work in pretty much any programming language as long as it has support for things like lambdas, functional programming stuff. Right, so turtle graphics. For people who are not familiar, you have a little turtle on a screen or a canvas, and you can move it forward, and then you can turn it around, and you can move it around. So basically, you can turn it and you can move it. So this is our API we're going to be using. You can move a distance, you can turn an angle, and you can put the pen up and pen down, and if the pen is up, it won't draw a line. If the pen is down, it will draw a line. So that is really simple API, and let's see how many ways we can make this really complicated, okay? We're going to make it as complicated as possible. By the end, it's going to be so complicated. So we're going to start with 3 different approaches to start with, and I've got a little bell here. Next, okay. So number 1, okay, object-oriented. Number 2 is abstract data type. Number 3 is functional. So object-oriented turtle. So an object-oriented turtle people are probably familiar with. You have the data and the behavior combined into one thing, which I'm going to call a tuple. And the thing about OO is you focus on behavior, right? You don't focus on data, and you encapsulate the state. So that means no setters and getters. If you have setters and getters, you're not doing proper OO, sorry. So here we have our client, and we have our turtle, which is a class. And the turtle contains mutable state. It contains its own state encapsulated that you're not allowed to look at. So I call the turtle and I ask it to do something, and it doesn't give me really back a response, and I call the turtle to do something else, and it updates its own internal state every time I do that. So let's look at the implementation. So this is going to be an OO, so it's going to be a class, and I have to have the internal states, various fields for position, angle, and whether the pen's up and down or not. And then I have my methods move, turn, pen up, and pen down. So that is my kind of API. And notice that I have to use the keyword mutable in F# because F# being a functional language, things are not mutable by default. Everything is immutable by default. So if I do want to do mutability, I actually have to ask for it. It's a very unusual thing. It's normally a bit of a code smell if you're doing mutable data. So notice there's no setters or getters. Right, so how do I move something? So I'm going to log that I'm going to move, and then I'm going to calculate the new position to where I'm going to move to. And then if the pen state is down, I'm going to draw a line using the canvas. And then I'm going to update the state because I need to keep track of where I am. I'm in a new position now. That's the move implementation. This backwards arrow, by the way, is F# way of doing assignment. Because again, you don't normally mutate things. There's actually a special symbol to set a value, a mutable value. Okay, so we've got the logger and the canvas. Now these are global dependencies, and I've hard-coded them in the code. So that's bad, and we will fix this later on. But for now, I've just sort of hard-coded it. Let's look at the turn implementation. So again, I'm going to log it, and I'm going to do the calculation of what the new angle is, and then I'm going to, again, update the state. So it's now pointing to a new direction, and I update the mutable state to do that, and so on and so forth. The pen up and pen down, I just change the state. I don't actually do anything. And so these ones just updating the state. They're not actually doing something that is used later on. Now, how do I actually use this thing? Well, let's say I want to draw a triangle. So I construct a turtle, and then I move it a certain distance, and then I turn 120 degrees, and I move another distance and 120 degrees, and move distance again. So I should be back home at the 0 point facing north or whatever, right? So that is how you would write some code using an object-oriented turtle. So let me do a quick demo of this so you can prove you I'm not just making this stuff up. So here is my my turtle here, and I'm just going to move this here. Right, so I can move, and I can turn, and then I can move again, and I can turn, and I can move, and I can move, and move, and so on. So that's that working. And if I want to construct a thing like drawing a triangle, I can just write a little function that contains, or method that contains all the operations to run to do a triangle. But notice this operation is not actually a method on the turtle. I have to write it as a separate piece of code, and I'll talk about that in a minute. Okay, so the pros and cons. Well, everyone knows pretty much how this works nowadays. Everyone's familiar with OO. I was around long enough that people didn't used to know OO, and they had to learn it. It was the new hot, trendy thing, just like functional programming is or whatever. Anyway, the downsides of OO is it's a black box. It's a stateful thing. It's very hard to test. I've got no setters and getters. How would I test that the angle logic is working? How would I test that the moving logic is working? I can't really, because it's all kind of internal to the object. So a lot of people add backdoors. They'll add a getter and a setter, or they'll add some sort of thing where for testing only, there's some special thing, and that's not so good, really, is it? It's hard to work them. It's hard to compose them together. It's hard to move two turtles at once. If I want to have a whole set of turtles, it would be kind of tricky, right? They're not really composable. And if I want to do something like a user-defined method, like a triangle or a square, that's a separate thing. I can't really add it as a property of the turtle because it's encapsulated. So that's why in C# you have extension methods to do this kind of thing. So, but that's a kind of it's a workaround how object-oriented programming doesn't do this. And of course, we've got these hard-coded dependencies, which are bad. Now let's look at abstract data turtle. So abstract data types are where the data is separate from the behavior, but it's still basically the same idea as OO. You have this encapsulated state, and you have behavior that works with this state, and you can't really see inside the state. But in an abstract data type, the things are separate. So you have your data structure and you have your methods or actions that work on that data structure, and they're independent because you have some sort of opaque data structure. So if you ever worked with a file handle or some sort of pointer to some data structure that you can't actually see what's in it, then that's what an abstract data type is. So let's look at our turtle version of this. We have a turtle handle, I'm going to call it. So it's opaque. Nobody can see inside it other than the other turtle functions. So it's very similar. And then the behavior now, we have the API, but the API, the handle is passed into every single function in the API. So the APIs are, it's not object-oriented. You still have to pass in the handle, but you don't know what's inside the handle. So it's still kind of safe in terms of working with it. So again, things like file handles and stuff work the same way. And again, to use it, I can call it with the handle. Now notice in this one, the triangle, it passes in a handle. So the way you call a triangle is just the way you call any of the other ones. The handle is the first parameter. So you can actually add the triangle to the module of all the other actions, and the user really can't tell the difference. From their point of view, it works exactly the same way, which is different from the OO thing where you have to have extension methods. Pros and cons, very simple. It does force composition over inheritance. Because there's no OO, you can't inherit a turtle. And people are kind of anti-inheritance now, so it's probably a good thing. So you can't do inheritance. And the functions, like I say, they're free to be moved around. You can organize the functions in lots of different ways because they're not tied to the same, they're not tied to be part of the class. So refactoring is a lot easier. And again, you can add user-defined behavior a bit more easily. Again, it's still stateful, still hard to test, just like OO. Right, functional turtle. Whoops, I didn't ring the bell. Functional turtle. So functional turtles, things are immutable. And in function programming use, everything's a function. There's no methods. All the data is immutable, and there's no internal state. So you, as the client of the thing, you have to keep track of the state, which can be good and bad, as we'll see. So as a client, I call the turtle function, and it gives me back the new state. It gives me back where it's moved to and what the new angle is. And then I use that state and I pass it in, and it gives me back some new state. So there's this back and forth between me as the client having to keep track of what the state is. So again, if I look at the data structure, it's very, very similar, except this time it's not mutable. It's an immutable data structure. And so it can be public, really, because people aren't going to mess with it. I mean, there's no way they can change it, so there's no reason to see it kind of encapsulated anymore. And then here's my behavior. Again, I have these functions that take the state as a parameter and return a new state. So this is the difference between the other ones where the state is immutable. I'm not changing the state. I pass in the state, but like the output is a new state. It's a clone of the original one, but it's different, right? But I can't change the original one because it's immutable. So everything takes in a state as a parameter, and it returns a new state as an output. So if you look at the code for how you might draw a triangle, you take the first state, you pass it into move, and that gives you the new state, and then you pass that into turn, and that gives you another state, and so on and so forth. This is what it looks like drawing a triangle. Now, this is great for testing because it's very explicit. If I want to see, what does the move do? I pass in this state, and I expect, I can actually look at the output and see exactly what it is. However, it is kind of ugly and not as nice as the OO version. Can we make this nicer? And the answer is yes, we can. Because if you think about these functions where they have the state as an input and the state as the output, and I have another function with the state as input and state as output, I can connect them together by taking the output of one and feeding into the input of the other. And that is called piping in F#. And if you've done Unix pipes or Linux pipes, it's the same thing. You take the output of something and feed it into the input of the other thing. So if I use piping, I can take the output of the initial state, pipe it into the move function, and take the output of that, pipe it into the turn function, take the output of that, and so on and so forth. So this looks much cleaner. And this vertical bar with the angle bracket, that's F#'s pipe operator. It's not just a vertical bar, it's slightly different. So it actually looks much nicer now. And piping is really the standard way of doing things in F#, and it's becoming popular in other languages now. Other people use piping as well. So this is much nicer to read. And all that whole state thing has gone away. So it almost looks like OO code. Now, what's the advantage of functional programming? Much, much, much easier to reason about because everything's immutable. Much, much easier to test because everything's stateless. And things are composable. So if I have two turtles, I could easily just combine the two functions to make a bigger function that works on two turtles at once. So very easy. Now, the downside is the client has to keep track of the state. And of course, we've still got these hard-coded dependencies. So one of the things in functional programming is all the workarounds we use to hide the ugliness of keeping track of all this stuff. Right, next, let's do some more complex turtles. We're going to be working with state in a more complex way. We're going to be working with errors, and we're going to be working with async. So the state monad, this is a monad word, and this is all about how you thread state behind the scenes. So let's say we have a new requirement that there's some sort of boundary, and if you hit the boundary, you have to stop. You're not allowed to move anymore. So in terms of our API, we're actually going to return the actual distance moved, which might not be the same as the distance requested. So our API is going to return the state, but it's also going to return what you actually did. Okay, so it's going to return a pair of things. So if we look at the code, there's our initial state. Now we move, we get a pair back. We get the actual distance and the new state. And then we might make some decisions based. If the distance is not what we expected, we might log it as an error, and we might turn it so it doesn't hit the wall again or something. Anyway, so, and then we run the move again, and we get the actual distance moved again, and so on and so forth. So this is what it would look like, kind of the crude way of implementing this. So again, this is good for testing because I get everything's extremely explicit. There's no magic going on. If I want to test whether the move function hits the wall, I can pass in something near the wall, and I can see the actual distance is moved. That's fantastic. But it's really ugly again. Really ugly. So this return pair, this is annoying because it stops the whole piping. We can't use piping because we're not just returning the state that we can feed in, we're returning a pair of things, and we only, one of them has to go down, but the other one can't. So can we make this look nicer? And the answer is yes, we can. So this is one of the first tricks that functional programmers have, which is transforming a complicated function into another kind of function that works better. So our function has the state and the input, like the distance to move, and it's now got kind of two outputs, right? The new turtle state and now the output of the thing, which is the actual distance moved. And that's ugly, but what we can do is transform it into a function which has just a one input, just the input parameter, and it returns a new function. So the second parameter, the turtle state, is actually saved for later. So this thing of turning a two-parameter function into a one-parameter function which returns another one-parameter function is called currying, really common in functional programming. So if you think about our turtle function, like our move function now, we have it, you pass in the distance and it returns this new function. It doesn't return the actual distance moved, it returns a function which has the state as a parameter. And we can then take that function and give it a name. We're going to wrap it up and call it state. Okay? But now what we've done is we have this function has a one input and one output. So this is good. It sounds like we can sort of start piping them inputs and outputs together. Now, I actually have a whole talk on state monad called the monadster. So it really is just, I'm really just skimming the very surface here. So obviously, if you don't understand what's going on, don't worry about it. I just want to show you the concept even, the basic idea. Now, what you can do is a nice trick where you can create something called a state expression, and it will hide the state behind the scenes. So with a state expression, it will keep track of the state for you, and you write the code as if the state wasn't there anymore. So you notice that I can say move, and I'm not passing the state in. And when I get the actual distance moved, the state isn't there anymore. So I'm working with everything other than the state. The state is sort of being threaded through behind the scenes. So I can write all the logic I did before, but without having to worry where the state is. So this is called a state expression. It's something that F# has. And actually Haskell and Scala, most functional languages have an equivalent. Haskell has do notation and Scala has for comprehensions and so on. So it's a really, really common technique because it's such an annoying problem in functional programming that people have developed tricks to work with it. So this is the F# version of that. Now, if we look at the original OO version, where if the distance is wrong, we're going to log an error. And if we look at the state expression version, where the distance is wrong, we're going to log an error. It looks exactly the same. It looks not exactly the same, but it's very, very close. So it looks very similar to the imperative version, but there's a big difference. The big difference is the OO version the state is mutable, and I can't test it because it's not actually returning the state, right? It's just doing it. Now, in the state expression, this version, it is actually returning the state. So if I wanted to take this function, I could test it on its own, and it would return the state. So it is actually much, much more testable, but when I use it inside this kind of states expression, all that state logic is hidden away from me. So I can actually use it like as just regular programming, but it's keeping track of that stuff. So much more testable, and you use this trick, and it sort of looks like the original imperative version. So pros and cons of state. It does look imperative, it preserves immutability, functions are still composable, functions are easy to test. Downside, it's much harder to implement. Now it's getting kind of tricky. Okay, next. Error handling, same kind of thing. We have a turtle function. This time, instead of always returning something, it's going to sometimes return successful and sometimes it's going to fail. So in functional programming, we don't normally throw exceptions if it's for simple errors. We return a choice, which is either it succeeded or it failed. It's okay or it's an error. And if it's okay, there's some data with the okay, which is the state. And if it's an error, there's some data with that, which is the information about the error. So I like to call these choice types because it's a choice between two things. In F# they're actually called discriminated unions, and other people might call them SUM, S-U-M types. But they're really, really useful for domain modeling. In my book, my domain modeling book, it's all about this stuff. It's very useful. So let's look at the implementation with this. So, given the actual distance moved didn't match, I'm going to return an error, and that's out of bounds, say. Or if it did work, I'm going to say everything's good, and I've just updated the state. So it's either success or failure, basically depending on whether it worked or not. So the nearest equivalent of this in OO would be something like an enum, or maybe subclasses with each different data in each subclass. It's not a standard feature in object-oriented languages. So again, we have the same thing. If I try and use it, I get the result. If it's an error, I have to test every single time. I have to do this kind of switch statement or a match statement. Is it an error? Is it successful? Okay, I do it again. Is it an error? Is it successful? And again, this is the correct way of doing it, but it's really ugly to use. So behind the scenes, this is going on, but is there a way to simplify it? And the answer is yes. We can create something called a result expression. And in this case, the result logic is hidden behind the scenes. So every time you do something, if it's an error, you kind of skip everything else. So if it succeeds, it's good. And if it's an error, it kind of skips the rest of the code. So behind the scenes, the error handling is being done, but when you write the code, you can sort of focus on the happy path. So this is called the result expression. And like I say, the errors are handled. It's not like you're ignoring the errors, the errors are managed behind the scenes, but you don't have to see them when you write your code. You can focus on the happy path. So that's good. And I have a whole talk about this called railway-oriented programming. Now, notice we still have this ugly state everywhere. We keep passing in the state to every single function. Can we fix that? Yes, we can. We can combine them together and have a thing which is the result and the state. And now we're getting back to this sort of standard imperative model that we had in the OO thing. But unlike the OO version, every single thing here is doing error handling, is managing the state, everything's immutable, it's really easy to test. So it looks like imperative code, but it's actually not. Okay, so advantages, again, we're not using exceptions, we're actually returning a choice between success or failure. It's almost like returning a Boolean. Everything looks like a happy path, but we are handling errors properly. Again, it's a little more awkward to use, but there we go. Okay, next. Async turtle. So what if the turtle was actually a physical turtle that was moving around the room, like a Roomba or something? You'd have to make a call, and let's say it's an asynchronous call. So you don't actually get the state straight away, you have to wait for the state to come. It's a callback. So given that it finishes, I get the new state, and I make another move, and then I have to wait for that to finish, and I have to wait for that to finish, and I have to wait for that to finish. And this whole thing of these nested async callbacks is really common problem. And you know, this is just the problem with async. It's really messy. And this actually has a name, which is the pyramid of doom, because these nestings get bigger and bigger and bigger, and you've got 10 callbacks, and they get really bad. So everyone thinks this is, this is the right way to do it, but everyone thinks this is really ugly. Is there a nicer way of doing it? Yes, there is. So there's something called an async expression, and again, it hides the async logic behind the scenes. So, and then I've got the state in here. Right. Now, what's going on behind the scenes is very much equivalent to the async await that you get in C#. And I think other languages are beginning to add this feature because it's a really cool feature. It hides all the nastiness of async stuff. And again, we've got the state logic. Let's get rid of the states, blah, blah, blah. So we have an async state. And so often in functional programming, you have these things kind of piled together. You have an async state result. And so you're still working with all this stuff, but you're handling the errors, you're handling the async, you're handling the state in a very nice way. Right, so this pattern is called monads. So the monad is just a generic sort of pattern for handling these things behind the scenes, these effects like results and errors and async and stuff. It's just a common way to handle these things, to chain these things together in a nice looking way so your code looks much nicer. So that's what monads are for. So we're using a lot of composition, right? Because everything is an output, you can always pipe it into the next function. We've got a lot of explicitness, right? Everything, there's nothing hidden inside the object. All the state is explicit. There's no mutation. All the errors are explicit. There's no exceptions. So doing this stuff does make it look ugly, but then we have these special techniques to hide the ugliness with monads and computation expressions and things like that. So monads, these are all three things we're using monads. Next. Right, now let's talk about decoupling. So we'll talk about batch processing, actor model, event sourcing, and stream processing. Right, so we've got all this state working, going around. So one way is to hide immutable state from you, which is the OO way. The problem with that is very hard to test. The next thing is for the caller to keep track of the state everywhere, which is the functional way, which we've been doing so far. But there's another way, which is to have someone else deal with it and not be your problem. And that's nice because it's not your problem. So we'll look at a couple of ways of doing that. We're going to look at batching, we'll look at agents, and so on. So let's start with batches. Batch. How does the batch process help you avoid the state? Well, what we're going to do is we're going to have a special intermediary now that's a batch runner, and we're going to send it a command, and it's going to do the running of the turtle for us, and it will keep track of the state for us. So we'll start with batches because that's the simplest one. And it's going to run, and we're going to send it, do this, do this, do this. It's going to loop over all of them and keep track of the state for us while it runs it. So that's how it runs. Now, we're going to send something down the wire, if it's a remote call. How do we convert a function into data, which is called defunctionalization? That's another buzzword you'll hear a lot. So these are the functions that I want to call in my API, but I can't really send a function down the wire. So what we do is we create a choice type, which is a one-to-one correspondence with the functions that we want to call. So for the move function that we want to call, which has a distance parameter, we're going to create a choice called move, and it's going to have a distance parameter. And then the turn function, which has an angle, is going to have a choice called turn with an angle. And this second one is a data structure. It's no functions, it's literally just a data structure. Again, you could think of it as a bunch of subclasses. So these choice types pop up all the time. You serialize them, put them away, and you pick them up on the other end. So here's a bunch of commands that I want to send to the batch processor. And these look like functions, but there's actually data, right? So these are the same, 6 different data structures put into a list, sent down, serialized and sent down the wire. Now on the batch runner side, it picks one of these things off the wire, and for each one, it actually does the turtle operation. And it's a one-to-one correspondence between what the choice was and what the turtle function is. So if I get a move, I call the turtle move. And if I get a turn, I call the turn function and so on. So this one-to-one correspondence between the data structure and the list of functions. And it's really common, back and forth between functions to data and then data to functions. Very common trick. So there you go. They're literally paired up, designed to be exactly the same. And then to run the whole thing, I just start with initial state. And for each command, I execute that. And that gives me back a new state. And I just loop through things, and I pass the state through each command in turn. And that gives me the final answer. So that's, again, the batch runner is handling all the state for me. So that's the mutable version. And if you're a functional programmer, you'd use fold, which is the immutable version of a loop. So that's the kind of imperative version, and that's the functional version. And by the way, if you ever do get into functional programming, I highly recommend learning all the collection classes, because collection functions, there's hundreds of them, and they're all really useful, this fold and map and all this stuff. Right, so pros and cons. What's nice about the batch thing is I don't care how the turtle works, right? I'm just sending it these data structures, and how it actually works behind the scenes, I don't know. It's a lot simpler to work than monads for managing state. You have somebody else manage the state for you, and your code is very simple. This is batch-oriented, so I can't make a decision based on the response. So if I move something and it's not allowed to move, there's no way I can make a decision based on that. So this is, we'll talk about a way of fixing that in a minute. There's no control flow. Right, now, actor model, basically the same, except it's real time rather than batch. So the actor model is very similar, except that you communicate using a queue, a message queue, right? So I put the command on the queue. The actor is reading from the queue and then processing each event as it comes in, each command as it comes in. So again, the actor has its own internal state. And this is a great way to work with mutable state in a nice, clean way, because nobody's allowed to touch. Again, it's encapsulated. You have to send a message to the actor to actually do something. And because it's queued, it's linear. So only one person at a time is changing the state. So you're not going to have any issues with having to lock things or having any kind of race conditions or thing like that. So that's really nice. So here's the actor. It reads from a queue, and if the queue's empty, it blocks, right? Because it's just a big loop. And then it does literally the same thing. If it's a move, data structure, we call the move, and so on and so forth. And then it just goes back to the beginning with the new state and waits for the next command to come in. So again, very similar logic, which is why I put them right next to each other. Right. Yeah, and the loop, now the state is just put through I don't need to have the mutable state, because the state just comes around for the next time in the loop. So here I'm calling it post, rather than I'm actually posting this little thing, because I'm posting it to a message queue. So each one of these things is actually going to work in real time. As soon as I send the message, hopefully it'll pick it from the queue reasonably quickly and actually do the thing. But if I send too many things, because it's queued, it's decoupled, it's buffered, it's async. If the actor goes down or has to reboot or something, it doesn't affect me as a client. It just means my stuff is buffered for when it comes back up again. Right, pros and cons. It's decoupled in space because it's a remote service. It's also decoupled in time because it's it's buffered, it's asynchronous. It's still, again, simpler than state monad, so that's nice. Extra boilerplate needed though, so that's not so good. Right, event sourcing. All right, now, what is event sourcing and why is it useful? So all these things, the state has been stored in memory. So what happens if you crash? how are you going to you really want to persist the state after each action, right? So how are we going to do that? So event storing is an event, you could just store it in a database, but event sourcing is a great way to do this kind of thing, because what you do is you store events, you store the journey, not the destination. You don't store the final result. If you look at this chess game, you don't, in a chess game, you don't store what the final result of the game is. You want to know, how did you get there? Who played which move at which point, right? So those moves are events. And if you want to record a chess game, you want to record all the individual moves. You don't just want to have the final state of the board. That's not very helpful. Here's another one. Let's say you have a bank statement, right? I mean, it's nice to know how much money you have, but it's also nice to know what went in and what went out, and how much, what you spent things on, right? So those are the events. Anything to do with money is typically event sourced, right? Any kind of accounting thing, you add an event every time. You don't just like store the final amount of money that you have. So it's a really common technique. So we're going to store the events, and every time we want to do something, we're going to load up all the events and rebuild the state from the source. So if we go to the bank example, if I want to know what my current balance is, I literally load up all my events for this month or whatever, and then that gives me my current balance. So I mean, there's ways to optimize that, but in general, you can always do that. And then after we process something, we create a new event, and we add that to the event store. So here you go, I send a command. So I read up all the previous events, like in the chess game. I load up all the previous events from the chess game to get what the current state of the game is. And then I execute the command, and then that might give me a new event, which I then save back to disk. Right? And then that loop just keeps going and going. So that's how event sourcing works. So a command, event and command are not quite the same thing. When I talk about commands, it's like I want you to do something, it's imperative. I'm asking you to do something or ordering you to do something. But that doesn't always happen. So that's what I want to have happen. An event is what actually happened. I actually moved this distance. I actually turned this angle. I actually did this thing. Because just because I want it to happen doesn't mean it actually happened, right? So pros and cons of event sourcing. Again, it's very decoupled. It's stateless, so it's very easy. It's very good to crash any kind of system which you need to crash and recover. It's very good if you need audit trails or any kind of compliance, any kind of traceability, because you have every single thing that happened. And if you want reports, of what people did, like classic on a website, where did they click, right? Not that just they ordered this thing, but what other things did they click on before they ordered this thing, that kind of thing. So much more complex. Every time we do something, we're going to get more and more complex. Storing stuff, events can be tricky. If you modify the data structures, it can get tricky with the versioning. Stream processing. Right, so, oh yeah, I need to ring the bell. There we go, stream processing. So we've talked about event sourcing, but this is like event sourcing, but we put the things on a stream. We don't just store it in our local database. We publish them for other people to look at. And what that does is it means that I don't actually have to do the actual work. I can say, I've done this thing. Somebody else can decide that means they need to move the piece on the board. I mean, a good example is a chess game. The chess game, that was just a list of events. So if I'm replaying the game myself, I physically read the event and I physically move the piece to kind of replay the game. And then I get another event and I move the piece. So I am reading the stream of events and actually physically doing something based on receiving those events. So it's quite common that you have people who generate events and other people who consume the events and some people who transform events. So you have this whole system. So let's say we have an event stream coming in and we have that's coming from upstream somehow. And then my little process is like, not all the events are relevant to me. So I'm going to filter out a lot of them and only focus on the ones I care about. Maybe I only care about turtle commands and I don't care about other commands that are coming down the event stream, right? So I'm going to handle it. I'm going to put it in the event store, just like we did with event sourcing. But this time, the event source is also published for other people to read. So there can be another person downstream who is now seeing these turtle events happening, and they say, oh yeah, I'm interested in turtle events. I'm going to actually do things with these turtle events. So again, it's more complicated, but sometimes it's quite useful. Where you have each person interprets the events and creates new events for the next people down the stream to read, because it allows you for a lot of decoupling. It's like one processor can focus on just the business logic for this thing, and someone else can focus on what do I actually do when I get the event. I might need to, call an API or do a transaction or whatever. So that's how it works. So let's look at the turtle example. So I sent a command, and it writes the event store. but I'm not actually going to move the turtle. I'm just going to record the event. And then what I can do is I can have downstream processors that work on those events in different ways. So for example, I have an auditing processor, and all it does is log the fact that that turtle event happened. So that's my audit trail, right? I can have a canvas processor which takes all these events and draws them on the screen. And then I have maybe a distance, maybe I don't want to run out of ink. So I have to keep track of how much ink I've used. So I keep track of how many miles the turtle has done, and that will give me a report on the total distance. So and it doesn't care about, the distance processor doesn't care about turning the turtle, it doesn't care about pen up and down, it just cares about did it actually move, right? So I'm actually going to do a demo of this in a minute. But the important thing is that the upstream processor does not actually move the turtle. All it does is it does the business logic for how a turtle might, for the events of moving a turtle, but it doesn't actually move the turtle. It's only the canvas processor that actually draws on the screen. So let me go a demo of this. And I know I'm going really fast. I promised you I'd be going fast. So here we go. Right, so here is our auditing processor. Right, there's the event stream. And the way I'm going to act on the event is just if it's a moved event, I'm going to log it. And if it's a turned event, I'm going to log it. And I'm going to say this is an audit trail. Okay, so that's it. That's the auditing. Now, the canvas processor is going to handle the same event stream. And it's going to filter the events to only moved. I don't care about, I'm just going to draw lines on the canvas, right? I don't care about the angles and all that stuff because it's already figured out. The upstream has already figured out all the angle stuff. It's just literally, I'm going to draw a line from here to here. So to act on a particular event, I'm just really going to draw a line. So this one is not actually doing any of the turtle logic about, where should the line go to and should the pen be up and pen be down. That's done upstream. All this does is handle drawing lines, right? So it's decoupled. This is what I'm saying. Is the logic of doing stuff is now decoupled from the action of doing it. And here's our distance travel processor. Again, it's using the same event stream. And again, it only cares about moved events. It doesn't care about turning or anything. And all it does is accumulate the distance so far and print it out. Right, so here is my command handler. And there are no events. So there's my event stream. There's my auditing processor, my canvas processor, and my distance processor. And they're all subscribing to the same stream. So again, I can have multiple things all working on the same stream. Right, so there's my little canvas again. And I'm going to turn, and I'm going to move, and I'm going to turn, and I'm going to move. Right, now notice, you see the distance traveled so far is 300. So it's successfully doing that. The auditing is keeping track of the moving, and it's keeping track of the auditing, and the canvas one is generating the canvas. So, and if I can look at the event, I can look inside the event store and see what events I've got. So there's my moved event, there's my turned event, there's my moved event, there's my turned event, and so on and so forth. This is because I'm using floating point, it's rounded it. I need to fix that and make it more rounder. Right, okay. So if I used so if I didn't have the canvas processor and I just did the distance processor, it wouldn't show on the screen. So let me do that, see if I can get that to work. I'm just going to do the distance processor and see if it works. No, because I need to. Why is that? It's not. I think I've got a hard-coded global variable, but in theory, it will actually keep track of the distance, and it won't actually do the canvas because I never registered it. Right, so that's stream processing. So you can see it's getting more and more complicated. Right, I said it's going to get more complicated. So it's event sourcing with extra work. But the extra work, again, is it worth it? It's worth it if you really want to separate if you really want to decouple the various things. If you want to decouple the logic part from the actions that you take, and it may be that you need to take multiple actions and different systems work on actions in different ways. So this is very microservice friendly because each of these stream processes could be a microservice. So people using, I guess, but people use Kafka this way, and they use RabbitMQ, and also, I mean, I'm not up to the latest thing, but whatever it is, people use it. Now, of course, it's more complex, so don't do this just because it's cool. I would never do this unless I really, really, really needed to, because it's really complicated. But it's going to get even more complicated. We haven't finished yet. Okay. So in these last few turtles, we've talked about, conscious decoupling. We're passing data around rather than passing functions around. And notice that the data store is also immutable. So that's one of the things about event sourcing. Unlike a kind of regular database where you replace what's in the database, we're adding to the database. So what's in the database already never changes, which is great for an audit trail because I guarantee that I'm never erasing anything. There's a famous expression, accountants don't use erasers. They never erase or delete anything. They always just add a compensating thing or a replacement or a refund or whatever, right? They never change the original data. Right, now let's look at dependency. So I talked about hard-coded dependencies. Now let's look at some ways to get rid of these dependencies. So we've got dependency injection, dependency parameterization, and dependency rejection. So what are all these things and how are they all different? Right, dependency injection. So we have a turtle class. This is typically an OO technique. We have a class and we have to, we need a canvas and we need a logger. So what we're going to do is create an interface for the canvas. We're not going to pass a direct canvas, and we'll paste an interface in, an interface for logger. We'll pass that in typically in the constructor, and then the methods in the object can use these dependencies that we've passed in, right? So this is very standard. I'm sure you're all familiar with this. Now, what's interesting is that the move function needs the canvas and the logger, but the turn function does not need the canvas, and the pen up does not need the canvas. So one of the problems is that you have this big interface and everyone has access to it, but maybe they shouldn't. And it's quite easy to have accidental coupling when the pen up starts using the canvas by mistake because there's a bug, right? So anyway, you've got interfaces. I'm sure everyone knows how this works. Construction injection is really used. One of the problems is the interfaces, you're doing a constructor and it's like, I just need one more method. So I add it to the interface, and the interface tends to get really, really big. You might have hundreds of methods, like the canvas, there might be like 100 methods on that canvas, and I'm only using one of them. I'm just drawing a line. Why do I have access to those other 100 methods, right? So it's, it's easy to do because I don't want to, it's like easy to add something to the interface than add a whole new thing. But you have these guidelines, don't do that. Interface segregation principle and single responsibility principle, all this stuff, don't do that. But it's so easy to do. So it's really hard to kind of stick to it. And, if I have access to some of these functions that I'm not really supposed to have access to, because they're right there, I could accidentally call them by mistake. And you end up with this coupling when you're ever trying to refactor something and things got tangled up where they shouldn't have been. And of course, typically you need an IOC container or something to manage this stuff. Right, next, parameterization. So this is the functional approach. And we have a move function, which has a distance parameter, and a turn function with an angle parameter, and the pen up function, which has no parameter. And what we're going to do, rather than hard coding the logging, we're going to literally pass in 2 extra parameters for what it needs. So the move function needs to log something, and it needs to draw a line. So I'm literally going to pass in a function that it can log, and I can pass in a function that you can use to draw a line. And the turn function only needs to log something. It doesn't need to draw a line, so I don't pass it in as a parameter. And the pen up function, only needs to log something, it doesn't need to draw a line. So the move function originally had 1 parameter, now it has 3 parameters. And the turn function has 1 parameter, now it has 2 parameters and so on. So we're literally just adding it as parameters. This is nice. And what's really cool about this is that these are functions, these are not interfaces. I don't have to create an I thingy, just an I canvas. I can literally just pass in a function for drawing a line. It's really simple. And the turn function has no access to that. So I can't accidentally have the turn code be dependent on drawing a line because it's not being passed in. So it's less buggy. And finally, if you start having too many, let's say I have like 20 different dependencies, that's going to be 20 different parameters. And that's really ugly. And it stops you. It's like, maybe I shouldn't do that. So it's the exact opposite of interface segregation. It's like, the natural inclination is to have fewer parameters. So you're much more likely to have better structured code because you kind of separate the dependencies. It's really easy to have hundreds of methods on an interface, but it's really hard to have 100 parameters. It's really ugly straight away. So it kind of keeps you honest without having to have some sort of code review, Right, so here is my move function, and I'm passing in the logger, just the info part, and I'm passing the canvas draw line. It's not any, none of the other canvas functions need to be passed in for this particular one. And so I create these, pass in these extra parameters. Now what's interesting is that the move is a 3-parameter function, but I'm passing in 2 of the parameters, and this is called partial application. A common technique in functional programming where I can just pass in some of the parameters and the other parameters handled later. So the state is going to be handled later. I'm passing in the dependencies, but not the rest of it. So when I have these kind of partially applied functions, I can use them just like I did before. The move function and the turn function, they look just like the previous ones, except now they are got the dependencies being passed in rather than being hard-coded actually into the implementation. So that's that. I'll skip over the demo, I think. The advantage of this approach is that it's really obvious what the dependencies are. Every function has dependency is passed in, unlike with an OO, where it's not obvious which method requires which dependency. You have to kind of look inside. With the functions, it's explicit on the outside. Like I say, functional programs love explicit stuff. These are functions, not interfaces. We don't have to create a special interface just for this. We literally just pass in we can pass in a lambda. We don't have to do anything. And like I say, it's a counterforce to having too many dependencies. So no special libraries, no IOC container, none of that stuff. It is hard to work with sometimes if you have nested functions, because you have to kind of parse it all the way down through the tree. So there are better ways to do it. And the better way to do it is something which I call, or it's called dependency rejection, which is the next topic. So dependency rejection. What does rejection mean? That means don't have any dependencies. How can you write code without any dependencies? I will show you. And this is a phrase coined by Mark Seaman, who literally wrote the book on dependency injection. And so he's now anti-dependency injection. He's pro-rejection. So what does it mean to reject dependencies? Obviously, you do need to have dependencies. You have to have some sort of I/O, but you keep it away from your business logic, okay? So rather than mixing your I/O with your kind of logic, you keep them separate. Keep your I/O at the edges, sometimes called functional core imperative shell. And if you do this, there are lots and lots of benefits for not having any kind of I/O in your code. Because for one thing, anything to do with I/O is non-deterministic. If you read from a database or read from the network or whatever, you don't know what you're going to get. Makes it very hard to test. If you have all your code be completely deterministic, every input has the same output, it makes it really easy to test. And so you get rid of the I/O that way. So you keep your non-deterministic code at the edges, and you keep your pure deterministic code in the middle, right? So you get the kind of sandwich effect. So the classic one is you load some data from a database, you make some decisions based on what you're going to do, and then you do something. The I/O is then write the stuff back to the database or actually do the thing, like move the turtle. We're going to see that in a minute. And if you do it this way, from a testing point of view, it's great too, because the unit tests are the stuff in the middle, and they are completely deterministic. They don't have any I/O, so they run fast, and they're very, very easy to write. And integration tests are the things with the I/O. So people say, where are the boundaries between integration and unit testing? If you do it this way, the boundaries are completely obvious. Right, so let's look at our original move implementation. We have the logger and the canvas. This is our dependencies, right? And then the rest of the stuff is our deterministic code, calculating the position and all that stuff. And then they're all mixed together like this. So if we separate the decision logic from the I/O, so what we're going to do is we're going to not actually write the message to the log. We're going to figure out what message we want to send to the logger, but we're not actually going to do the logging. And then similarly, if we're going to say, if we wanted to draw something, this is what we would draw, but we're not actually going to do the drawing. We're going to make a decision about what to draw, but not actually draw it. So if the pen is down, we want you to draw something. If the pen is not down, we don't want you to draw something. And that is the decision we're making. So this code, and then we return all these decisions back to the next step. So this code is completely testable because for any input, I always get the same output, right? There's no databases, no I/O, there's no canvases, nothing like that. So super, super easy. I can test the log messages, I can test the pen logic and all that stuff very, very easily. So we've replaced anywhere we had I/O, we've replaced it with a decision. We return the decision. And then we have an impure piece of code which does do the I/O, which kind of wraps the original one. So we do our decision, which is pure, and then we do the I/O. So based on the decision, what are we going to do? Well, the decision said, print this log message, so I'm going to log that message. The decision said we want to draw, so I'm going to use the canvas to draw. Or if the decision said don't draw, then I'm not going to do anything. So this thing, this very simple change, has separated the pure decision logic from the I/O non-deterministic logic. So it's very, very similar, but it's much more testable now than the original one was. So we got to our wrapper with the pure business in the middle and the I/O on the edges. So that is dependency rejection, and I think I've got just enough time for this. Right, there's my turtle class. Where is my? Oh, that's not the one. I want the. Oh, it is rejection. Where is it? Right, so here is my unit test. Right, so I create my turtle, and I put the pen up, and I do the decision part, so I can test the decision, and you can see that it says don't draw anything. Okay, and then I put the pen down, and I do the decision. I do the decision again, and now it says, yeah, I want you I want you to draw something. So from a unit testing point of view, this is my unit test. So all the logic, the complicated logic about which angle to turn and which direction to move and all that stuff, that is completely testable. And then my integration test is using the whole thing. So rather than using the pure code, I can now use the imperative, the stuff with the I/O in it. And that's literally, I can now open up the canvas and run the same code. So it looks like it's running the same code, but the difference is that anything to do with I/O is now kind of been separated from the business logic, and it's easier to test. Right, next, interpreter. All right, 2 more to go, and these are the most complicated ones, of course, for last. Right, now if I look at the APIs, my turtle API originally said, move here's the distance I want you to move, and here's the current state, and then I'm going to give you back the actual distance moved and the new state. And then for the angle, you give me the angle you want to turn and your current state, and I'll give you back the new state, and so on and so forth. So that's my API. Now, at some point later, I say, actually, I really want to do some error handling. So I'm going to change these things to be results instead, because it's going to maybe have an error case. And actually, it turned out that we need to make this async as well. So it's now an async result, and so on and so on. So every time I do this, I'm messing with the API. Every time I do this, I'm breaking the caller, and the caller's getting annoyed with me because I keep changing my mind. So is there a way to design an API that does not have anything to do with async or results or anything like that? That is all hidden. And the answer is yes, there is. Now, we saw how to do this with the batch thing, where I sent a command over the wire, or the actor thing, where I posted a command to the actor, but that didn't allow me to do any kind of logic based on the response. Well, the actor one you probably could do, but the batch one you couldn't. So let's look at another way of doing this, which is called the interpreter pattern. And what I'm going to do is I'm going to send an instruction to the interpreter. And this is called the interpreter pattern because it's just like an interpreter that interprets a program, right? So I send an instruction, and it's going to run that instruction, and it's going to give me back a response. Now, I actually then will based on that response, I will then send it another instruction, and it'll give me a response, and based on that response, I'll do another instruction. Now, the trick is I have to send all this at once. So I actually have to send it as a data structure. And how can I send all this stuff as a data structure? So here's how I'm going to do. I'm going to have a choice type. And you notice there's 2 groups. There's the input and there's the callback. So what it says, I'm going to send this distance parameter. This is what I want to move. The interpreter is going to run it, and it's going to give me a response. Now, how am I going to handle that response? I also have to pass in a callback, just kind of how you do async. I pass on a callback that the interpreter will run, and I will then use that callback to figure out based on the response what to do. So that's the input, and then I will get this back from the interpreter, and based on that, I will pass the interpreter another program. And it is like a program because this is basically a set of instructions. And so again, this is really complicated, but sometimes it is useful. And you need at some point, unlike the other ones, you need to say, okay, stop interpreting. So you need a stop instruction as well. Right, so how do you actually use this thing? Well, let's say I want to draw a triangle. I say move this thing, and the interpreter's going to run it, and then what's the callback? Well, the callback is based on the actual distance I wanted to return. Okay, and then the callback says, well, there's no response from that one. So based on that, which is I don't care, I'm going to move, and that's going to give me another actual distance, and so on and so forth. So the way you write it is a whole bunch of callbacks mixed with these data structure. So this whole thing doesn't actually do anything. It's just a giant data structure with lots of operations or instructions. And when you've finished writing it, this draw triangle does not actually draw a triangle anyway. It's literally a big data structure. So now I can interpret it to do different things. So almost like the stream, very similar to the stream processor idea. And of course, this is really ugly. And it turns out there's a way to hide this, just like we did with the other one. There's a kind of hide that we can write this turtle program expression thing. And so you can actually write the code that looks much more like imperative code. Right, so we got our turtle program. Now let's interpret it. So I can have multiple interpreters for the same program, just like I had multiple stream processors for the same stream. So let me open that one up. And there is an example of my program, right? So unlike the batch one, I can actually do logic. Like if this is the distance coming back from the interpreter, and if the distance is less than 50, I want to print an error message, and then I want to turn and do and so forth. So you can actually write imperative code. And again, this looks really ugly with all these kind of callbacks passed in. But as you saw, we can get rid of the callbacks by having this super duper expression thing, just like we got rid of async callbacks. So this is the kind of turtle program, and all the callbacks are gone. So it looks like imperative code now. Right, so this doesn't actually do anything. Like I said, it's just a program. So if I run it, it's just a data structure. So let me interpret it as a turtle. And it's going to draw it on the screen. Right. But now let me interpret it the same thing as the distance interpreter. So it's the same program, but this time it's just going to interpret it as a distance. And it's just going to add up all the distance. So it literally is writing a little piece of code, and you're writing your own mini interpreter and your own mini instruction set. And it's a lot of extra work. Why would you do that? Well, the first thing is it's completely decouples what you actually do behind the scenes, because it's an instruction set, and how the instruction sets get executed, you don't care. So all the thing about async and errors and stuff, that's behind the scenes. You don't really care about it. So it really is the purest possible API. The other thing you do is optimization. So if I make a whole bunch of moves to the turtle, 3 moves in a row, because it's a data structure, I can do, just like you do compiler optimization, it's like I got 3 moves in a row, I can collapse it into 1 move, right? Or if I have a whole bunch of things, if it's a kind of remote call, I can batch all those move operations. If it's moving a turtle and the turtle takes 200 milliseconds to reply, I can batch all the moves into one single send, so I get faster responsiveness. All these. Maybe I'll save money in the amount of network traffic. Who knows? But you can do a lot of things with optimization if you want to. So if you really, really care about it, if you're Facebook or Twitter, this is the kind of thing you would do, and in fact they have done. If you're the average small business, you do not need this. So it's really, really complex. It really only works best if you have a limited number of operations, like, I've got 4 operations. If you had hundreds of operations, it would be bad. But if it's just like, fetch a URL, upload something, it's like 3 or 4 different things, it works great. Right, last one, capabilities. And I'm going to run a few minutes over, I'm sorry, on this. Right, so let's talk about our API again. Now, one of the problems when you call an API is sometimes it doesn't like what you did, and it gives you back an error message. And one of the problems with that is, it won't let you do something, but it's not telling you what you can do. It says, no, you can't do that. It's like, well, thanks very much, but I want to, what can I do? So it might say, I try and move the turtle. It says, you can't move the turtle. It's like, well, what can I do? Oh, well, the API doesn't tell you. So the capability model flips it around, and it returns what you can do rather than just giving an error for what you can't do. So that's the whole thing about a capability. So what I mean by a capability is like a key for a lock, right? So if I have the key, I can open the door. If I don't have the key, I can't open the door, right? So what happens is when I make a call, the server or whatever the API gives me back a bunch of keys, and each key is something I can do, right? And I'm calling these capabilities. So then I use one of the keys to open the door, and I'm now in a new room, and I get back some more keys, right? Now maybe some of the keys don't, this time I don't have some of the original keys, so there's things I can't do which I could do before. So let's, for example, moving a turtle. So I get back, when I move the turtle, I get back 3 keys. I can move it again, I can turn it, I can put the pen up and down, right? So I move it again. Now this time I hit the edge. So it's going to give me back 2 keys. It's going to give me back the turn key and the pen down key, but it's not going to give me the move key. I can't move. I literally don't have the capability to call the move function. So this is very different from like a regular API where you can call any API call at any time. This is literally, I can only use the API it gives me. So the API is kind of dynamic, right? The actual functions available to me change based on the result of every single call. So here's the turtle capabilities. So typically I'm using a data structure here. Mostly I can do the other ones, but the move function is optional because sometimes I can do it and sometimes I can't do it based on whether I've hit the wall. Right? So these are the keys. I've got 4 possible keys I could get back. So every time I do something, I call an API, I'm not just getting a result, I'm getting back a list of capabilities for my next call. So let me do a demo, and then we'll be done. Right, so let me see if I can do it. Here we go. Right, so I'm going to initialize the canvas, and I'm going to move. Whoops. Now, if you notice here, this is the capabilities that came back. I have my data structure, and there's 4 capabilities, and the move function is available, and the turn function is available, and the pen up function is available. Okay, so now I'm going to move, and the move function is still available, so I can call it again. Now I've hit the wall on the canvas, and the move function is no longer available, so I literally have no way to call the move function. It's not available for me to call. I can do the turn function, and if I do the turn function, maybe it will move, will it? Let's see if I turn. Yeah, so as soon as I've turned, the move function is available again. So now I can move. So what this is really good for is things where the logic is really complicated and the client doesn't need to know what all the logic is. I mean, sometimes, often you have the client has to all the rules, like this button should be enabled, if you clicked here, this button should be enabled, and if this is bad, you can't do it. Sometimes the logic can get really complicated, and why should the client know all that? And if the client has the logic hard-coded just like the server has, now you have a synchronization problem between the logic being in sync between the business logic being in sync between the client and the server. So in this model, the client knows nothing. It doesn't know about whether it can move or not. All that stuff is not there. And for example, if it ran out of ink, if I added logic about you're not allowed, if you run out of ink, you can't do anything, I could add that to the logic here, and the client wouldn't care that I added new features. Or the pen is broken and you can't move the pen anymore. I could totally do that, and the client would not care because all it does is it knows it's just given these keys and it runs the keys. So it's a very powerful technique. So no business logic shared. Another good example, if you're playing a game of chess, right, and there's the rules of chess, the client, you could just give back all the possible moves that you can make, right? So you give back, here's 15 moves you can make, and I pick one of the moves and I run it, and then it goes to the server, and the server comes back with, here's 10 moves you can make. So as a client, I don't need to know the rules of chess. It just gives me, here's all the moves I can make, and I pick one. The complicated logic of what moves are available and what moves are legal and stuff, as a client, I don't care about that. It literally is going to give me all the possibilities. So this is also better security because I can't do bad things, right? One nice thing about capabilities is you can transform them. So because it's a function, I can say this capability is only available during business hours. And if you're doing it, at night, you can't call it. Or this capability is only available to you, and it's not available to anybody else. So all that kind of stuff is super easy to do with capabilities. So again, the downside is very complex to implement, and the client has to change the way they work. So rather than just like calling the API, the client has to go through all the possible capabilities and say, which ones can I use? and then, present some user where they can click it. So if you've heard of hate AOS, OAS, hypermedia as the engine of application states, that is exactly the same model, and I have a talk about that. So if you were doing this for a website, you would return capabilities as a bunch of hyperlinks. And each thing you could do would be a hyperlink that you can click on. And so you might, you might do something like this where you literally can't see, you've no idea what it's doing. This is the URL you call to make a move. And it's completely, it's very safe because nobody knows what that code is, So that's a capability-based way of web stuff, like say hate OAS. Right, okay, that's it. Last one, thank you very much. I'm going to try and put all the code on GitHub, Wlaschin/turtle. There's nothing up there now, but it's going to be in a minute. And thank you very much for coming.